For years, the MH370 satellite handshakes were often shown as large arcs across the Indian Ocean. But before we can understand the path of the aircraft, we first need to understand what a handshake signal actually is. A handshake is not a GPS position. It's a timing measurement between the aircraft and the satellite. Every time the aircraft and satellite communicated, the system measured how long the signal took to travel there and back. That timing created a distance relationship. Distance rings expanding outward from a signal source. The arcs are not flight paths. To understand MH370 satellite data, we first need to understand what these arcs actually represent. These are called BTO arcs, burst timing offset arcs. Each ring represents a measured signal distance between the aircraft and satellite. The signal traveled from the aircraft to the satellite and back again. By measuring how long that took, the system could estimate distance. The farther the signal traveled, the larger the arc became. Each handshake created another distance boundary. The aircraft was not flying on the ring itself. The ring only represents where the aircraft could exist at that signal distance. The challenge was never simply drawing arcs. The challenge was determining how the aircraft continuously moved through them over time. The satellite system itself was stable. Once the satellite handshakes established distance through the BTO arcs, investigators then had to examine how stable those measurements actually were. This graph shows the measured BTO error behavior over time. Each vertical spike represents variation between the measured signal timing and the expected timing calculated from the satellite geometry. This first clip is the raw coexistence phase. The red waveform represents the dominant stability layer of the signal environment. The blue waveform represents the embedded continuity behavior hidden inside that larger structure. The beginning of separation between dominant stability and embedded continuity. Now the blue signal starts becoming smoother, more coherent, and more directional. At the same time, the red structure still exists, but the viewer begins recognizing the continuity path underneath the noise. This is essentially the filtering phase, or continuity extraction phase. BTO error environment evolving over time. The red waveform shows the dominant stability envelope of the satellite timing system, the larger signal environment surrounding the aircraft communication path. Each fluctuation represents variation between the measured signal timing and the calculated timing expected from the satellite geometry. At first glance, the signal appears noisy and unstable, with spikes and rapid changes occurring continuously throughout the timeline. When we compare the original BTO error graph to the reconstructed signal environment, an important pattern begins to emerge. At first, the original measurements appeared chaotic, a dense field of spikes, timing variation, and overlapping signal behavior. But once the signal is reconstructed as a continuous waveform environment, we begin recognizing that the same structure was already present inside the original data. The reconstructed red stability envelope now closely mirrors the overall shape and density of the original BTO error field. What initially appeared to be random noise begins revealing organized timing behavior surrounding a stable continuity carrier. The blue core signal remains centered through the middle of the environment, showing that beneath the larger fluctuations, a continuous underlying structure was always present inside the handshake system. This is the critical transition point in the analysis. The goal is no longer simply plotting individual handshake measurements, but understanding how the dominant stability environment and the embedded continuity signal interact together over time. As the two views begin resembling one another more closely, the apparent confusion inside the original graph starts resolving into a recognizable signal structure, transforming isolated spikes into an evolving waveform relationship. The red signal field still contains individual fluctuations and isolated events, but the white curve exposes the dominant trend running through the center of the data. Instead of disconnected measurements, the signal now behaves like a continuous waveform system moving around a stable equilibrium. The majority of the BTO behavior naturally concentrates toward the center of the structure, while larger deviations become increasingly rare farther from the core. This is where the analysis begins transitioning from raw observation into signal interpretation. The chaotic appearance of the original handshake environment starts collapsing into a measurable continuity pattern, revealing that beneath the spikes and short-term variation, the system was continuously operating inside a structured timing relationship. As the signal structure becomes clearer, a second behavior now begins separating itself from the surrounding noise. The blue continuity waveform starts emerging independently from inside the larger red signal environment. Even though the dominant stability field still contains spikes, variation, and short-term disturbances, the blue line continues maintaining its own smooth, directional behavior through the center of the data. This is an important transition in the analysis because the continuity signal is no longer completely hidden inside the chaos. Instead, it begins revealing itself as an independent structure operating within the larger timing environment. The red field still represents the overall signal variability and dominant envelope behavior, but the blue continuity carrier now demonstrates that a stable relationship persists through the middle of the system despite the surrounding fluctuations. What initially appeared to be random handshake noise now starts behaving more like layered signal interaction. The outer red environment reflects the dominant timing variability, while the blue waveform reveals an embedded continuity structure moving through it independently. Rather than isolated spikes, the signal begins behaving like multiple interacting layers evolving together over time. At this point, the continuity signal is no longer simply existing inside the waveform. It is now demonstrating directional continuation through the signal environment itself. The yellow directional marker highlights the transition point where the embedded continuity carrier continues progressing forward while the dominant red stability field begins collapsing toward equilibrium. This becomes a major visual shift in the analysis. Earlier, the signal appeared dominated by spikes and instability, but now the blue continuity waveform maintains a smooth, directional descent through the center of the system, even while large red disturbances continue occurring around it. The yellow arrow emphasizes that the continuity relationship persists independently from the surrounding noise and continues evolving through time. What makes this important is that the signal now begins behaving less like a random statistical distribution and more like a guided continuity path moving through a structured timing field. The dominant red environment still reflects the larger BTO variability, but the embedded blue carrier demonstrates stable progression through the system, revealing continuity, direction, and persistence hidden inside the original handshake behavior. The next stage of the analysis begins introducing progressive filtering directly onto the original BTO environment. Instead of forcing the signal into a final shape immediately, the waveform is processed step by step through multiple continuity-preserving stages. Each layer reduces instability while retaining the underlying timing behavior hidden inside the original handshake structure. The raw signal begins with dense spikes, rapid fluctuation, and short-term timing variation. As outlier removal and smoothing are introduced, the larger instability begins collapsing inward, while the dominant continuity relationship remains preserved. Rather than destroying the signal, The filtering stages begin exposing the stable timing behavior already operating underneath the noise. Stages of filtering and continuity extraction. Each color layer represents a different phase of stabilization, beginning with raw, noisy measurements and progressively moving toward structured continuity recognition. The lower processing stages show how the signal evolves from raw data through outlier removal, smoothing, trend extraction, continuity lock, and finally into stabilized structure. Rather than destroying the original signal, each stage preserves the underlying continuity while reducing short-term instability and random variation. The multiple colored waveforms begin converging toward one another, revealing that beneath the noise, the dominant signal behavior remains remarkably consistent across each processing phase. The vertical yellow continuity tracers now behave like an Etch-a-Sketch continuity recorder, tracking the signal one step at a time as it progresses forward through the waveform environment. This becomes important because the signal is no longer behaving like disconnected handshake events. Instead, it behaves like a continuously evolving motion structure, where continuity persists across every filtering stage. By the final structure phase, the underlying waveform relationship becomes stabilized, measurable, and directionally coherent through time.